Okay, so in the last class, we have discussed analysis of short circuit current waveform on alternator. So that is, we have discussed three cases. So transient, transient, and okay, transient, transient, and steady state. So we have discussed the corresponding circuits also. In the subtransient, we can see that XAD, XF, and XAD, where XAD is armature resistance and reactance, and XL is leakage reactance, and XF is field reactance. So once the subtransient time period is completed, then this damper winding effect will be nullified, and we can see the resultant circuit as XAD and XF, and here XAD will be nullified, and this reactance is ignored in the transient case here. This transient case exists for 2 to 5 cycles, and again in the steady state, this XF field reactance is also the effect of field reactance is minimized, and so that it is also ignored, and we can see the final circuit as the XL is in series with XAD. XL in series with XAD. Okay, and even we have discussed alternators connected to the infinite bus bar. In the last class, we have discussed what is an infinite bus bar. When there is no change in the terminal voltage and input frequency, irrespective of the consumption and delivery of the power to the bus bar, to or from the bus bar. So if there is no change in the voltage and frequency and speed, irrespective of the power consumption and power delivery to the bus bar, then we can say that that is the infinite bus bar. And we have discussed that. So we need to see that the purpose of reactive power is to maintain the area flux constant. Whatever I have written in the last class, everything is remained same. And we need to see that the purpose is to maintain the area flux constant in any machine. So here in synchronous machine, we can able to either deliver or consume the reactive power. So we can see the three cases here. This is the reactive power formula here. Q equal to V by X into E cos delta minus T. So when E cos delta is greater than V, then we can say that it's overexcited. When it is less than V, then we can say that it is underexcited. When it is equal to V, then we can say that it's a normal excitation. In overexcitation case, it is having more than the sufficient amount of reactive power, then it is going to deliver to the bus bar. So that is what we discussed. So here it is delivering the extra reactive power to the bus bar here. Okay, and in the underexcitation, so it is not having a sufficient amount of reactive power to generate the flux here. That's the reason the machine is consuming the reactive power from the infinite bus bar. So that's the reason we can say that it's an underexcitation, and we can say that the type of magnetation, it is magnetation, and here it is demagnetation. In the normal excitation, the reactive power is sufficient to generate the required amount of flux in the machine, so that it is neither delivering the reactive power nor absorbing the reactive power. That we can say that it's a under excitation. So here, the purpose of reactive power in the power system is, I would like to add one point here. That is, so here we can see that nearly 80% of the loads, 80% of loads are inductive in nature. Am I correct or wrong? 80% of loads are inductive in nature. Loads are inductive in nature. So that is induction machines, or all the this fans, all these are inductive in nature. So when these loads are inductive in nature, the power factor decreases. To improve the power factor, so I need to have I need to have power factor correcting devices, so that I need to deliver the reactive power to the system bus, so that the power factor is maintained constant. Just I'm giving the brief review. If the power factor is decreased, then what are the effects? Can someone tell me what is going to happen to the active power, and what is going to happen to the reactive power? Need your responses.
Reactive power increases.
Yeah, reactive power increases. Thank you. And active power decreases, which is not acceptable. And so we need to see this. We need to see that the active power should be increased and reactive power should be minimum, which is sufficient to energize the system here. Okay, and that's the reason we need to have certain reactive power delivering devices like capacitor and synchronous machine also capable of delivering the reactive power, or else it can also capable of consuming the reactive power. Okay, consuming the reactive power. Now we will try to see the effect of now we can see the effect of change in excitation. Effect of change in excitation. So this is under loaded condition. So here, what is going to happen here? If the field excitation, the field winding voltage is varied, then what is going to happen here? So this is we are considering under the no load condition here. So we have the equation here. Normally, E equal to generated voltage. E equal to generated voltage and V equal to terminal voltage. Okay. So E equal to generated voltage and V equal to terminal voltage. So we have the equation we already discussed this Q equal to V by Xs into E cos delta minus V, which is already discussed in the previous units itself. Now let's assume that this is a synchronous machine and it is connected to the infinite bus bar. Under normal excitation, when the excitation is normal, that is when the excitation is normal value. So we can categorize, as we discussed in the previous cases, there are three cases here. One is normal excitation, and second one is over excitation, and third one is under excitation. So under normal excitation, what actually happens here? This E cos delta, as we discussed in the previous class, what is happening here in the normal excitation? E cos delta is equal to V here. The same condition that I'm using here. So under normal excitation, E cos delta is V, and cos 0 equal to 1. Then I'm assuming that the delta value is approximately equal to 0, so that E is equal to V here. E is almost equal to V here. And we have the equation. We already have the equation that E equal to V plus J into IAXS. E equal to V plus J into IAXS. Generated voltage equal to terminal voltage plus IA into synchronous reactance, XS. What is XS here? Synchronous reactance. Okay. So by rewriting this equation, so IA equal to, so E minus V equal to J into IAXS. So IA equal to E minus V by XS. So this is the IA value here. As E equal to V, then what is happens here? E minus V equal to 0. So what is the armature current here? 0. Am I correct or wrong? So under normal excitation, what is happening here? The generated voltage is equal to terminal voltage. Or else we can also say in the other manner. This is, let's assume that this is a terminal points of A and B. When the voltages of VA and VB are both are same, then will there be any current here? The current will be 0 here. So the same is happening here. When IA is equal to 0, we have the formula active power P equal to VI cos phi and reactive power equal to VI sin phi. This when one of the component is 0, then total active power will be 0 and reactive power will be 0. So under normal excitation, the active power will be 0 and reactive power will be 0. We can able to say that condition, when both powers are 0, we can say that condition is nothing but floating on the bus bar. We can able to say that condition is floating on the bus bar. You will have a objective Viva question if they want to ask you that. What is the floating on the bus bar condition? That is, when the alternator is connected to the bus bar, then there is no active power and reactive power flows from the machine, or from the machine to the bus bar, or from the bus bar to the machine here. Just it is connected ideally. So both are having the equal voltages. So this is the generated voltage and this is the terminal voltage. For your information, generator voltage is E and terminal voltage is V here. This is the terminal voltage. These three terminals is terminal voltage. Okay. So under this condition, there is no power transfer. Active power and reactive power transfers are not taking place here. So that's the reason we can say that it's a floating on the bus bar condition. Floating on the bus bar condition. This floating on the bus bar condition is taking place under the normal excitation. Okay. This is one of the previous competitive exam question. So under which condition floating on the bus bar is taking place? Options are normal condition, over excitation, normal excitation, over excitation, and under excitation. So the answer is normal excitation. And second one is overexcitation. In the overexcitation, we can see this E cos delta is greater than V, and obviously then the generated voltage is greater than terminal voltage. So here all these conditions we already discussed that what is overexcitation. Here in the overexcitation we can see this, it is demagnetization, okay, and the power factor is lagging power factor, okay, and Q is positive, okay. So here we can write here demagnetization, lagging power factor, and Q is positive. So what are the conclusions that we made in the previous class? Just we'll try to correlate here. So here under the overexcitation, now IA, now what is happened to the IA? Can someone tell me, is the IA value will be 0?
No.
No, IA value is not equal to 0. So that IA lags V by 90 degrees. So here, as I'm saying that lagging power factor, so ZPF and the pure excitation, we can say that it is lagging by 90 degrees here. So here the machine is operating under the ZPF. So if you want to make a phasor diagram, you can see this. So V and E here. So with respect to voltage, what is the current here? Current is lagging by 90 degrees. Okay, and here as okay, let me try to rewrite once again. So this is V, okay, and this is IA. So why I am drawing back here? It is ZPF lag here. ZPF lag 0 power factor lag 90 degrees lagging. Now here I need to represent one more component, E equal to V plus J into IA into XS. So here already have represented V phasor here and IA phasor. So now I need to represent IA XS. So to perpendicular to this IA, this will be the okay. Now this is J into IA into XS. Now this V and this J into IA XS together we can able to say that this total value is equal to A. This is the phasor diagram. This is the phasor diagram here. So here we can see that if I substitute that T equal to VI cos phi, what is phi value here? Phi value is equal to 90 degrees, cos 90. And what is the value here? 0. So the reactive power will be 0. And sin 90, 1. So reactive power will be maximum. So here I can say that under the overexcitation, only reactive power, under the overexcitation, only reactive power is delivered to the bus bar. Delivering or observing, what I said in the previous class, when Q is positive, it is delivering, reactive power delivering to the bus bar. Reactive power delivering to the bus bar here. So that's what I have specified. What I have specified. Now coming to the under excitation. So the condition is same. E cos delta is less than V. And here in the under excitation, what is the points that we need to note down here? Q is negative, and magnetization, and current is ZPF lead, and IA is not equal to 0. So E cos delta is less than V. So E is less than V here. So what is the effect of armature reaction here? It is the effect is purely magnetization. The same phasor diagram I am representing here. So okay, this is V phasor. To this V phasor, the current is leading now. Current is leading by 90 degrees. 90 degrees lead. That's the reason I am representing ahead of voltage. Now I need to represent this IA axis. To represent IA axis, so this IA axis is represented. this IA axis is represented in the opposite direction. When this is IA, then IA axis will be downwards. So here this value is IA axis, and what is the resultant value here? This value is E here. The same is represented here. This component is V. So V, and this is in phase opposition. IA axis is in phase opposition. IA axis is in phase opposition. Okay. Okay. So here P equal to, so here so here so what we discussed that phi equal to 90 degrees. So cos 90 is equal to 0. So active power is 0, and reactive power sin 90 again 1. So reactive power exists. So under the over excitation, we can say that over excitation, under excitation, normal excitation, P equal to 0, active power equal to 0. Okay. Under the normal excitation, Q is equal to 0. Under the normal excitation, Q equal to 0. Under normal excitation, Q equal to 0 here. Okay. And in this case, under excitation, the reactive power is absorbed from the bus bar. As we already discussed that Q is negative. Whatever the conclusion that we made in the previous class, the same conclusions also I'm deriving. Okay. So this is the effect of excitation under no load condition. You can expect the another external exam question. Explain the effect of change in excitation under no load condition connected to the infinite bus bar. Question will be, explain the effect of excitation when alternator connected no, when alternator connected to infinite bus bar. That can be